All right, problem 3. Let's see. Problem 3 is the one where you're looking out the car window. The rain is falling vertically, so I'm going to draw my raindrops in blue. So rain is falling vertically, like this. And you are looking out the window of a car. Here's your car window, and your car window is moving horizontally. And so what you see in the car window then is the rain makes streaks along the window, because you got, the rain has some horizontal relative motion to your car, even though the rain is falling vertically, because the car is moving. And so what you notice is that you notice the rain is making streaks of 45 degrees with the horizontal. So the streaks are like that, and the horizontal is like that. It's a 45-degree angle. And then at the end of, then the car accelerates for a bit. Car A equals 2 meters per second squared for 15 seconds. Car accelerates. That makes a little sense to it. So what happens is you look outside, see these 45-degree raindrops, the car accelerates at 2 meters per second squared for 15 seconds, and at the end you notice that the angle has changed, and now the angle of the streaks is 30 degrees. And that's all you know. You know the rain is falling vertically, the car is moving horizontally, and these streaks are... Okay, so here's the way I look at this problem. This is a relative motion problem. We have 3 velocities we care about. One is the velocity of the car with respect to the ground, which we know is horizontal. Okay, so I can say V CG, car with respect to the ground, equals, and it's all horizontal. So what we can do there is we can just say the magnitude of VCG times I hat is the VCG vector, because it's all in the I direction, right? Okay, the velocity of the rain with respect to the ground, and that's going to be magnitude of rain with respect to ground, and it's all vertical, right? So it's all J hat, and it's going down, so it's negative. So just to be absolutely clear here, let me draw my coordinate axes in. There's my X and my Y. And then finally, we have the velocity of the rain with respect to the car. And that is going this way. So is, something is some magnitude, and it's going like that. So it's going down this way and making an angle of theta with the horizontal. So if we want to just do a little sketch of this vector is going purely horizontally to the right? So it's like that. This vector is going purely vertically down. So we want to figure out how to, hold on a second. Yeah. No, it's all right. Nah, it's all right. That was Mr. Hannum asking me for more copies of the worksheet. So let's see if we can. Where was I going? So let's see how we can make an equation that uses these 3 vectors. Now remember we're using the notation we learned in Giancoli, or wherever you learned it from, where you have your velocity of the car with respect to the ground is CG. So it's the thing you're talking about the velocity of, and then what you have it with respect to. So, and the rule is you can add 2 things to make something else if you can put like the near subscripts together. So in this case, we can match the C up on the end of this one with the C at the beginning of this one. So we can say VRC plus VCG equals V, and then the way it works is you take whatever you have in common in the middle and smack it out, and just take this and this, VRG, and that conveniently is also what we've got. So this, I gotta tell you, that using this system and remembering how this works is very powerful. I use it myself. This is not, relative motion gets real tricky when you've got one thing moving, another thing moving a different way, and you're trying to find the velocity of something with respect to something else. It gets really tricky, and learning and just sticking to this notation system can really save you. So anyway, but we've got this. So we've got this vector addition equation, and that's all good. But can we draw a picture to represent this? And you can solve this algebraically with some work, but I think it's much easier if you do the picture route. So VRC plus VCG equals VRG. This velocity of the rain with respect to the car is going down this way, right? So as the car is moving to the right, the rain is making these streaks that point off this way, towards the back of the car, going down. And then, so we're adding that to the velocity of the car with respect to the ground. Well, the car is going this way, right? So there's our velocity of car with respect to the ground, and then velocity of the rain with respect to the ground. So goes straight down. And that makes sense with our vector addition, right? Because this vector plus this vector equals this vector. And that's how you do vector addition in, graphically. You do tail to head. So tail of this vector, head of this vector, yoink, yoink, and then this one. So this angle, here's theta. This is, I'm just going to label these with their magnitudes, so that's why it's scalar. VCG. Okay, so what do we know now? We have a theta, we have an angle measurement here, and they tell us two different ones, and we have velocity of the rain with respect to the ground and velocity of the car with respect to the ground. So what's great here now is that theta relates these. You can take the tangent of theta and relate these two things. That's the trig function you go to when you want opposite over adjacent. So now you can say tan theta, and let me make a better A, tangent of theta equals VRG over, and even that's kind of ugly, let's make that a little better there, VRG over VCG. And now the beauty of this is that we have our two different situations. Initially it's a 45-degree thing, finally it's 30 degrees. So at the beginning, we'll draw a picture for, let me draw a slightly better angle, there we go. All right, so there we go, and they add up to this. So initially this is 45 degrees. This is velocity of rain with respect to the ground, or speed of the rain with respect to the ground. It's just a scalar, it's a magnitude, but and then initial velocity of the car with respect to the ground. So I'm going to call that VCG 0. Okay, well, what's the tangent of 45 degrees? Tangent of 45 degrees, let's see, is 1. That's just, that's what it is. It's a 45, 45, 90 triangle. Remember, this is a right angle, right angle, etc. So, this is a 45, 45, 90 triangle, so the two legs are the same. So, then the initial velocity of the car must equal the speed of the rain with respect to the ground. Hopefully I'm not out of bounds here. Hopefully you can read this. So these two are the same. The car initially starts driving horizontally at the same speed that the rain is falling vertically. That is a significant fact here. So, and we can use that because now if we go to the second one, okay, so the second observation is when the rain is making a 30-degree angle with the horizontal. So now this is 30 degrees, still falling at the same speed, right? Still VRG, and this is VCG. I can call this VCG final. So after the acceleration, and we know. Let's leave that there, and we know that. So taking this over here, let me just switch colors for fun. Let's do this like disgusting pinkish color. All right. So here we can say VRG over VCG final. That's all going to be equal to the tangent of 30 degrees. And the tangent of 30 degrees is, let me see if I remember this, 1 over radical 3, right? Yeah, that's right. 1 over radical 3. Okay, so progress now. So what's the final velocity of the car? Well, remember up here, the car was accelerating for 2 meters per second for 15 seconds in between these two observations. So what you can say is that you had some initial velocity of the car plus the acceleration times the time that passed equals the final velocity. So VCG 0 plus acceleration was 2 meters per second squared, 15 seconds, equals VCGF, which means, now, which this is 30, right? But then VCG 0, what's that? Well, remember up here, we figured out from the 45, 45, 90 triangle that the initial speed of the car was the same as the speed of the rain. So that means, right, because we have that right here, VCG0 equals VRG. So this is actually VRG plus 30 that equals VCG final. And now we bring that over here, plug that into there, and I'm just going to come over here and write it. 1 over square root of 3 equals VRG. That is a horribly disfigured looking. There we go. VRG over VCG final, but that's actually VRG plus 30. Well, now we're playing with fire because we got this is one equation with just VRG in it. So now it's just algebra to solve this, right? So let's cross multiply and get to VRG plus 30 equals root 3 times VRG, and then 30 equals VRG times root 3 minus 1. And so then, of course, it's pretty easy. VRG equals 30 over root 3 minus 1, and that's equal to about, I think it was like 41.0 meters per second is how fast the rain is falling, which is, faster than rain generally falls. So I admit it's kind of an unrealistic problem, but there you have it. I didn't think through it.